Hey guys, it's Mr. Ray here with our next lesson in polynomial functions in advanced functions. The last few lessons we've been trying to learn a little bit more each time about what kind of characteristics can we determine about the equation of a polynomial function. So we've learned things like end behavior. What does the extreme left and right of the graph look like? We've also learned things about looking at the degree, whether or not there's maxes, global max and min, also about the potential, the highest and the lowest number of x-intercepts, and the highest and lowest number of turning points. And some of the graphs we did in the last couple of lessons, to be honest, were a little bit, well, not very accurate in terms of detail. We kind of had to do a lot of guessing of what it could look like based on what we knew. So we're going to try to get a bit more detailed into exactness, okay? Now, when we were working at the equation in the first two lessons, we were looking at the expanded form or the standard form of a polynomial. Basically, all the terms are separate, no brackets, no factors, just terms added or subtracted to each other. So we're going to look at, instead of the equation in standard form, we're going to look at factored form. Okay, and that should give us some more very specific information that should help us. So how do we get the equation from standard form to factored form? Well, we'll figure that out later, but for now, let's just assume we can get the equation in factored form, and what will that give us? Okay, so a couple of definitions. Family of polynomial functions, okay? We did a little bit of this with family of quadratics in grade 10. This extends into all polynomials, so basically, if a set of polynomial functions, a family of polynomial functions is a set of polynomial functions whose equations have the same degree and whose graphs have the same zeros or x-intercepts. Okay, so basically the a value that's out front will basically be the stretch or compression or reflection characteristic that you saw with polynomials. So that will be the determining difference between the different family members. So if you had the exact same factors or x-intercepts and the same degree, you can see the similarities between the family members. Okay, it's just things are stretched or compressed a bit more. We can look at that a bit later. Now there's also this term about terminology of order. So the best way to describe that is with an example. So here's the function f of x, and it's already been factored. So we have two factors. One of the factors is squared, one of them is just to the power 1. So when we talk about these two different factors, we also talk about the order of the factors, and that order is exactly the same as the exponent. So this factor x minus 3 has order 2, and the factor x minus 1 has order 1 because there's an applied exponent 1 there. Eventually, once we figure out from this factored form, we're actually going to get the x-intercepts, and we could talk about the order of the x-intercepts as well. It matches up with the factors. Okay. Now, we did this in grade 10, 11. If you set your polynomial equation equal to 0 and it's all factored, it's in factored form, you can find the x-intercepts or the zeros by setting each of the factors equal to 0. So for example, if this was your factored equation, oh, sorry, that's not what this is. If you know your, if you know your x-intercepts or x1, x2, etc., or your zeros, you can create the factors from the zeros just by saying x minus each of the factors as its own factor. And then you have to, don't forget, this is always something that's missed out. There's an a value out in front. That's what I was talking about with the stretch or compression or reflection. Okay, so if you know all the x-intercepts and you know one other point, then you can plug in your x-intercepts into these x1, x2, x3, etc. And then you can, once you've got those done, you can substitute in the points. So the f of x would be the y value of the point, and then you'd sub in the x value of the point in each of the factors, and that allows you to solve for a. So this is very similar with quadratics. If you knew the two x-intercepts of the quadratic, you could set it up in factored form with the a in front, and if you know any other point, you could plug in that point and then solve for your a value. So that extends into all polynomials. Obviously, the equation is going to have more factors depending on what the degree is. Okay, so we'll be looking at that. If any of the factors of a polynomial function have odd degree, then the curve of, sorry, this should be, let's call this order, because that's kind of what the term we just introduced. So the order of the factors will actually be very helpful in determining how the curve crosses or passes or touches the x-intercept. Okay, so if a factor has an odd order, so if the exponent of the factor is 1, 3, 5, etc., then the curve actually crosses the x-axis, goes from one side to the other at that x-intercept. So we call these ones cross, at least I do. These, if it has an odd order for a factor, the curve will cross. Okay, if the factor has an even order, that is, it has the factor has exponent 2 or 4, etc., then the curve actually turns or bounces at the x-intercept. So it doesn't cross the x-axis, it kind of turns around and goes back from where it came from. And we'll see examples of that. So this would be a cross x-intercept, and this would be, I call these ones bounce, cross or bounce. And we can tell that by the order of the factor or the order of the x-intercept. If it's even, it bounces. If it's odd, it crosses. Okay, so let's do some actual work here. This says sketch a possible graph of the function, and this time you can see it's factored. So f of x equals negative bracket x plus 2, x minus 1, x minus 3, and that factor, we actually have two of them. So that factor has order 2, or the x-intercept that comes out of here will also have order 2. So first thing we're going to do, nice easy thing to always get, is the y-intercept. So the y-intercept, remember, you set the x equal to 0, so it's going to be f of 0. So basically, if you're plugging in zeros into these three spots, we're going to get the negative sign times 2, because the 0 plus 2, 0 minus 1 would be negative 1, and 0 minus 3 is negative 3, but this one is squared. Okay, now if you multiply these all together, so that would be negative 2 times negative 1, that's positive 2, and negative 3 squared is positive 9, so positive 2 times positive 9 is positive 18. So there's the y-intercept. Now the x-intercepts, we've been talking about those quite a bit for this lesson. So what we do is instead of setting x equal to 0, you set the y value equal to 0, because that is the x-axis. So you set the equation equal to 0. So I'll just put my equation back with a 0 on the left side. Okay, so if you remember this from quadratics, you just take each factor and you set each factor equal to 0. Find the value of x that makes each factor 0. Basically, that's what you're doing. So this becomes pretty quick. So from this information, you know the x-intercepts will be x equals, and then from here, if you solve that, set that equal to 0, that's going to be -2. So that x-intercept came from there. If you set x minus 1 equals 0, that means x has to equal 1. And x minus 3, set that to 0, then x is equal to 3. It comes from there. So that we've got 3 different x-intercepts. Now what I want to talk about here is the order, which is basically the exponent for each of the factors. So these 2 x-intercepts have order 1, and this one has order 2 because it's got a square there. Okay, so if you remember what we just talked about in the key concepts, when you have an order 1 x-intercept, the curve crosses the x-axis at that point, whereas the order 3, it bounces. Okay, so we're going to use those in a second. There's only a couple of problems when the equation's in factored form. One is the degree isn't obvious. Like you can't just point and say, oh, that's the degree there. You actually have to figure it out. So the way you do that, so the degree is equal to, so all we do is we take the number of x's we're multiplying. So from that x plus 2 factor, there's an x there. From that x minus 1 factor, there's an x there. From the x minus 3, there's actually 2 x's that we're multiplying because we're squaring it. So now if you look at the degree of this, if we actually combine these together, that would be x to the 4th. So the degree is 4. So n equals 4. And the leading coefficient, okay, people do this in a variety of ways. What I like to do is just multiply the coefficients of all the x terms. And we can't forget about that minus sign this time because, so we have, I'm going to make that a -1. I don't have to, but it just makes it more obvious what I'm going to do with it. And then that x, the coefficient is +1, so there's a 1. That factor, the coefficient is 1. And this one coefficient is 1. But don't forget we're squaring it. It's not going to make any difference really, but so that's the -1 from the minus sign up front. This is from the x plus 2 factor, that's from the x minus 1 factor, and this is from the x minus 3 factor. We put that all together, lots of 1's being multiplied, so we know the answer is 1 for sure, and we have that sole negative sign. So leading coefficient -1. So remember, these two things from the last couple of lessons, that's going to tell us a lot about the end behavior and the potential number of turning points and x-intercepts. But we don't need that. Well, at least we don't need the x-intercept part of what we've done, because this is telling us how many x-intercepts we have. So that overrides kind of the possible values of x-intercept that we get from the leading coefficient and degree. Okay, so I'm going to do my sketch here. All right, and make sure my scale's all right. So most of these x-intercepts are pretty close to 0. That number there is pretty big, so y-intercept of 18 I'm going to put up here. Okay, so we do know that there's x-intercepts at -2 and at 1 and 3. So there they are. Make them nice and bold. So those are the 4 points that we know from getting the x and y intercepts. Now, we also, based on the leading coefficient being negative and the degree being even, because it's 4, from the last lesson, we know that the end behavior looks like this. Okay, so I'm going to kind of running into my graph here, but so we do know that the graph will come down here and come down here. I'm just using this as a guideline for now. I'll actually put in a nice line. Okay, now I can't just kind of connect these yet. I have to look at the order of the x-intercepts because that's going to tell me does the curve or the line cross the x-axis here or does it bounce? So a bounce would be, well, I'll talk about that when I get to there. So order -2 and 1, they cross. So I'm just going to put a faint kind of line through to remind me that the graph is going to cross through. And at 3, it has, didn't write it in, order 2, and that means it's going to bounce. So how do you show that on a graph? Well, we don't know whether it's coming down here and bouncing or coming from down here and bouncing back down. So I just put these faint little 2 cups. So it's one or the other. We're not sure which one yet. Okay, so that's going to help me draw this. So at this point now, that's all the information we have. So you could start at one end and kind of work your way through. Now, I'm just for the sake of argument, those are the only x-intercepts, so it's not like we've left any out. So if the graph eventually comes down here towards -infinity, I can kind of connect this to the x-intercept at 3. And since I'm coming from down here, I can now kind of do my semi-final version of this. I do know it's coming up from here and it's bouncing off that x-intercept at 3, and that tells you that that's an even order because it's bouncing off. So that creates a factor either with order 2 or 4, and obviously we know it's 2 because we were given the equation. But you can also tell by looking back at the graph that factor has an even order. These factors have an odd order because they cross. Okay, so now you can kind of keep working your way to the left, and I'm only picking from the right to the left, just the way I felt like it for this question. You could have started here, worked your way through. Now, we have this x-intercept here at 3 and this one at 1. So one of the things that doesn't get talked about is obviously this is going to come down, it has to go back up. So that's like a local minimum going to occur there. Now, where does that minimum happen? Okay, how much do we know about that? Well, we actually, at this point, we don't know how far down it goes. So I can't just connect those like that and say, oh, that's definitely right. Or I can't go down here and say that's definitely right. We don't have enough information to say where that minimum would be in terms of how high or low. But we do know where it would be in terms of the x coordinate. If we take the halfway point or the average between 1 and 3, we do know that at x equal 2, somewhere along here is where you're going to get that local min. Okay, so again, it's just a guess. So if I draw my curve down here, just so it shows that we have that min at x equals 2, that's good enough. Okay, now this is going to go up, and it's going to go through 18 for sure, because we know that's the y-intercept. But we could do a little bit better than just connecting up there and coming back down. So again, I know when I come back down here, there's going to be there will be, in this case, it'll probably be a global max up here somewhere. It's not necessarily at 18. It could be, but we can tell for sure. So again, just like we found the midpoint between these two x-intercepts, this one's at 1, this one's at -2, so a difference of 3. So if we go 1.5 in between, I could just do like a little temporary dotted line here. That's telling me where this maximum will be. It's going to be along here somewhere. So that for sure tells you that that's not the maximum. So in order, if I'm coming up here, this is going to be below the maximum. I have to keep going. So I actually don't know how high to go, just like I didn't know how low to go there, but I do know it's going to be to the left of the y-intercept. So I'm just going to make an assumption it's there. So it's going to peak right there. And so now I'm going to connect those two together. And then, like I said, it comes up to here, which is the true maximum. And then it's going to come back down through. I didn't talk about these 2 points. These go through because we drew those lines because they're order 1. So when I didn't bounce off here, I'm not bouncing off here, I'm going straight through. And that lines up pretty good. You can look ahead and say, okay, it looks like this is going to go down through, and that lines up with the end behavior here. So if I do that, obviously I'm adjusting where my left arrow goes, and that's a pretty good job. We know these 4 points are exact. We know the end behavior is correct. We know that the local mins are global mins and maxes. We know what x value they have, but we don't know what y value they have. So we're guessing at that. Okay, so that's it's a much more accurate graph than if we had this equation in standard form, where we would get the y-intercept, we get the possible number of x-intercepts, possible number of turning points, but we'd really be guessing about actual x-intercepts and where they turn. This is actually pretty good. Okay, it's just some of the points we're guessing at, these 2 points here. Okay, so let's keep going forward. All right. So this question is giving you some information. It's not giving you the equation, but it's giving you the zeros. It's a cubic equation, so that tells you n equals 3. And we've got zeros at these 3 points, -2, 3, and 2/5. Okay, now it says it's a cubic function, and remember, a cubic, if whatever the degree is, that's the most number of x-intercepts or zeros. So this tells you it has maximum 3 zeros, and this gave you 3 zeros. So it's not like they gave you some of the x-intercepts and maybe left something out. These are the only x-intercepts or zeros. I kind of interchanged those words, as you noticed. Okay, so from this we can now start setting up our equation. Okay, the other piece of information we have is the x-intercept, or sorry, the y-intercept. That'll be used in a second. Okay, so I'm going to start writing my equation. Okay, now start off with f of x, or whatever letter you want. Now remember, we don't know the entire equation yet until we incorporate another point. Just knowing the x-intercepts or zeros gives us a family of equations. Okay, but to get that specific member of the family, we have to incorporate another point, which will be this, and that will set the a value, which is up front. So we always have to remember that a value that goes in front of the factors. All right, now when we build the factors from the zeros, okay, so remember it's going to be the opposite sign of these, and we can test it. So if it's the opposite sign, I'm thinking x plus 2, and you can easily check this. So if x plus 2 is a factor, if you set that to 0, you'd get x equals -2, which is the 0. So that works. Same idea here. This would be x minus 3. Okay. Now this one's a little different because it's a fraction. So you could put x minus 2/5, but you don't really want to have fractions in your factors. So here's here's how you get a nice looking factor. So I'll just leave a space for that. So if you actually had x minus 2/5 as your factor, this is just an aside here, if you multiplied, in order to get rid of that 5, I'm going to multiply the whole factor by 5. And when I do that, I'm not going to change the x-intercept. I'm just going to change what that factor looks like. So this would turn into 5x minus 2. And that's the factor that I'm going to use here. And you can always test it if you're not comfortable. If you set that equal to 0, you're going to get x equals 2/5, which is your 0. Okay? Now, if you didn't change it to this, okay, and you left it as x minus 2/5, when you solve for the a value, it's going to be different. Okay, so I'd really want you to do this conversion so that you have whole numbers here, not fractions. All right, otherwise, like the equation would be correct theoretically, because if you graphed it, you get the same graph, but you're working with different a values, and this is much more aesthetically pleasing when everything is integers and no fractions. Okay, so now that we've got kind of the template for the family of functions that go through these three, now we're going to get our specific equation for the member of the family that has y-intercept of 6. So if you remember, that means the y-intercept means it's the point 0, 6, so f of 0 equals 6. So we're going to plug that in to our equation that we have. So f of 0 is 6, so that goes f of 0 is equal to 6, so that's a 6 here. And then we set all the x's to 0. Five times 0 minus 2. Okay, so we have 6 equals a times 2 times negative 3 times negative 2. So if we multiply these out, we get positive 6 times 2, that's 12 times a, 6. And then if we divide both sides by 12, we get a equals 1/2. Okay, so what we do with that, we take this previous version that we had for the equation, but we didn't know the a value, now we do. So we plug that in to this original version. F of x equals 1/2 x plus 2, x minus 3, 5x minus 2. Okay, and just to make it official, is the equation in factored form. Now, you could expand these, and you're going to get a cubic, probably with a lot of fractions because of that 1/2 that you're multiplying with, at least a few fractions. So what form should you leave it in? Well, unless it says in the equation, write an equation in standard form, or if it tells you which form is needed, well, that obviously you have to convert it. But if they just say write the equation, well, that's an equation of this function, so we can just leave it like that. We don't have to expand it unless they tell us they want to do that. Okay. All right. This next question, they're giving us a graph, and from the graph they said write the equation of the function shown below, and then state the domain and range. Okay, so this is kind of the opposite of the first question. So what we're going to do is pull out the important points. So obviously we've got 2 zeros, x-intercepts. We've got this point that's given. Now, you might be tempted to grab the y-intercept, but it's kind of dicey how accurate it would be because it looks like it doesn't cross exactly there. We're really not sure because that's like 2.5 units for that one square, so I wouldn't be that comfortable using it. So the fact that we have this exact point, we definitely should use that and not the y-intercept. They gave us the y-intercept in the previous question, so that's why we used it, but you don't, it could be any other point besides the zeros that were given here, okay? That will give you the exact equation, just like it did with a quadratic in grade 10. Okay, so from here we know the zeros are -2 and 3. So therefore the factors in the equation would be x plus 2 and x minus 3. But then we got to think about the order, okay? Obviously this is not a quadratic, so it wouldn't just be that. So we look at the order of the x-intercepts. So you see both of these zeros both have order 2. So that makes it bounce. That's why we know it's order 2. I guess it might be order 4, but I don't think we'll have any questions in this course where you'd have an order 4 from a graph. We might talk about that later on. How would you know whether it's order 2 or order 4 by looking at the graph? But for now, let's safely assume that it's order 2, which it is. Okay, and the reason why we know is because, well, since it's order 2, we know it's order 2 because it bounces. We can now update our factors to x plus 2 squared, x minus 3 squared. Okay, so that we got quite a bit of information so far. So now if I start creating my equation, I've got f of x equals a, don't forget the a, and then we put in the factors here. These factors just define the family, not the exact function, x minus 3 squared. Now, here's where we plug in this point. So this point here is f of 2 equals 4. So 4 equals a, and now we substitute in x equals 2. All right, let's work this out. 2 plus 2 is 4. 4 squared is 16. 2 minus 3 is -1. -1 squared is +1. All right, so 1 times 16, so 16a. If we divide both sides by 4, we get a equals, sorry, we divide both sides by 16, we get 4/16, which reduces to 1/4. So we know that a value is 1/4. So we can create our final version just by changing that a to 1/4. The rest of it is all the same. So that's pretty powerful just by looking at the two x-intercepts, their order, and one other point. We can get the equation of that exact polynomial. Okay? We didn't even have to, if you think about it, we didn't have to look at the end behavior, which we could look at that and say, well, that's got to be even degree, positive leading coefficient. Okay, we can get that from the graph, but we didn't have to use that. We can actually confirm it. So it's got a positive leading coefficient, and you can see it's got total degree 4 here. So, well, at least the 4 matches up with the fact that it's even here. So that we can use that to kind of confirm our answer. Okay, the second part here, part B, state the domain and range. Okay, well, the first part is the easiest question in this unit. What's the domain of a polynomial function? It's always all real numbers because it stretches on forever. Okay, what about the range though? Sometimes it's everything, all real numbers, sometimes it's not though. So in this case, because it's a degree, well, it's a degree 4, which means it will have a minimum. So it's going to open up and have a minimum. What's the lowest this function can get? Since it does have a minimum, and both of these are at 0, so therefore we can see that every value of y for this function is greater than or equal to 0. Okay, hopefully that makes sense. So those are kind of fun questions to do. Just pull out the information from the graph to create the equation. And we have one more question. So this, we don't need this much room, it just happened to be the last question. Sketch the graph of x to the 4th plus 2x cubed. Well, this is in basically standard form. It doesn't have any factors here. So this is a fairly nice function or expression to factor because it doesn't have any constants. So you can see right away, well, I could factor out an x cubed from both terms. It takes out quite a bit, and we'd be left with an x plus 2. Okay, so we've got both versions of this polynomial function in standard form, factored form. I'm actually going to put brackets around this x. You're going to see why in a second. Okay, so now I'm going to look at these factors. I've got two different factors, one with order 3 and one with order 1. So from that I could say the zeros are at, now this one sometimes people will forget about because it's just x. Well, what makes x 0? Well, that's pretty easy. 0 makes x 0. So this gives you a 0 at 0. Okay, so don't forget, if you see an x as a factor, that's another x-intercept or 0. So a lot of times those get forgotten about and just focusing on these binomial factors. So this 0 at 0 has order 3 because of the exponent 3. And the second, this factor here creates a 0 at -2. And because it doesn't have an exponent, it's implied 1, so that's order 1. Okay, so these are both even orders. They're not the same order, but they're both even. So that tells me that they both cross at the x-axis. They both cross the x-axis. That's going to be helpful when we do our sketch. Okay, let's look for some more information because that's not going to be enough to sketch it. We're going to need some more information. So let's look at the leading coefficient and the degree, and that's going to give us the end behavior. So when I do that, I'm going to go back to this version, the standard form, or the expanded, you could call it as well, no brackets. So this has a leading coefficient of 1, so that means it's positive 1. And the degree is 4, obviously. Okay, so remember from the last lesson, that tells you that even degree, positive leading coefficient, that's the end behavior. Okay, and we do need one more point, because remember, if we just use this, that would give us the family of the family of polynomials that have these x-intercepts. We want the exact one for this member of the family. Okay, so in order to get that other point, we can just figure out the y-intercept. And there's a couple ways of doing that. You could plug in what's the value at x equals 0, because that's where the y-intercept is, so plug in zeros. That gives you 0. The other way of doing it is in the standard form of the polynomial, look for the constant term. Now there's no constant term here, at least it doesn't look like there is, but that means the constant is actually 0. So we got 0 as the y-intercept in a couple of ways. So 1 is evaluating, so 0 cubed times 2. Well, that would be good. Looking at that, forget that. Okay, so you could either plug in x equals 0 or find the constant in the standard form. So hopefully that makes sense. A couple ways of doing that. Okay, so that's actually enough information now. So I'm going to do my sketch down here. All right, first things we do are the zeros. So let's put a bit of a scale here. Okay, so we have a 0 at 0, and a 0 at -2. And we know from the order that they both cross. So I'm just going to kind of put faint lines through here to remind me so I don't have to look back and determine the behavior, what's going on there. Now the end behavior tells us that we already know it's going to come up here on both sides. Okay, and the y-intercept 0. Well, that's actually on the graph. So that raises an interesting point. If you have an x-intercept at 0, which we found here, that automatically tells you the y-intercept is 0. So that's a third way of getting that. Because if you have an x-intercept at 0, you have a point on the graph at 0, 0, which is also your y-intercept. So that point is an x-intercept and a y-intercept. Okay, now in terms of the, so I could, well, let me just do this. So we know it's going to come down here and cross here, but then it's going to have to turn back and come up here. So remember what I talked about. So this is at -2. So it's going to turn down here and come back, but remember the halfway point, somewhere along there is going to be where that local or global minimum is going to be. So I'm just going to pick a point so I have a reference as to where to head to. Now there's one other thing here, and this is the first time we'll see it. So in the previous examples, when we had an odd order, it was always the order was 1. When you have an order 1 x-intercept, the line that goes through it is a straight line, sort of like what we've drawn here. Now this x-intercept is order 1, so the line that goes through is going to be pretty straight. So I'm going to darken that up a bit. Now this one here is order 3. So how will that differ from there? If I just drew the line coming down here and up here, that looks an awful lot like a quadratic, right? So if you graph this on Desmos, you're going to see something different. And so if you have an order 3, so you're coming up from here. So I'm just going to draw the behavior here. I'm going to show you what it looks like. So it kind of comes down here and then turns, something like that. Okay, so you can see the difference. That's order 1 x-intercept. This is order 3. So I have kind of a term that I use. It kind of looks like this x-intercept has like a magnetic warp, like it kind of sucks it in towards and deflects it a bit. Okay, so the higher the actual order, the more that this is going to happen. So if you did have something with order 5, this thing is going to come way down here. Okay, like that. If you have order 1, it's basically a straight line. order 3 looks like you can see a bit of a warp. It's almost like the graph of x cubed. It's exactly the graph of x cubed actually. So that's why the graph at these two x-intercepts are a little different, because that's order 1, that's order 3. And now I'm just going to kind of connect the dots. So I know this is going to come down here, back up, and then this is going to head up to positive infinity, and so is this. These are really just for reference. Don't try to always join up to those. Just remind yourself of where you need to end up. So I'll just make a note here. Degree 3, 0 has, call it a magnetic warp. Just like it's being attracted towards it, and that pulls it from its path. And the order 1, so a degree 1, 0 has a straight line. Okay, so that's a new piece of information. If you compare this, our sketch, to a Desmos graph, it's actually going to look pretty close. Okay, there'll be a little bit of difference, but not a whole lot. Now, if you had something like, you might come across a degree 2, 0 and a degree 4, 0, and they differ as well in their appearance. So we'll see those in a future lesson, but you could look at a graph and determine and look at it and say, well, that's got a degree 2, 0, and that's got a degree 4, 0, just by looking at the graph. Just like how you can say that's a degree 3, that's a degree 1. Okay, so if you were building from here, you wouldn't really have to guess. You know this, they're both odd order, but you know that this has to be degree 1 because it's pretty much a straight line, and this is probably degree 3. It's definitely not degree 1, and then build your equation from that. Okay, so that's it for this lesson. In the next few lessons, we're going to be looking at, how do we use this new information of factored form to get the zeros and make a much more accurate graph. What if we only had the standard form, right? If you had something like, let me go back a couple of pages. Well, I guess we don't have anything along here. So, what if you had something like 3x to the 5th plus 2x cubed minus x squared plus 10? How would you be able to factor that? Because in grade 10, 11, we've really only factored quadratics. Okay, we had quadratic formula. We know all the simple trinomial factoring, complex, but we never looked at what if you had something longer? How would you factor that? So in grade 12, we're going to learn those tools so that I could give you a pretty complex looking polynomial function that's in standard form, and you could actually find its zeros. Okay, in this lesson, we were kind of given the zeros, other than this one here, where they gave us something easy to factor. Okay, but this is going to be a special case because we could factor this because it didn't have a constant term. Okay, so that's it. We've got homework assigned down here, so do your best at that, and see you on the next lesson.